Now we will continue examples on some basic points. Okay, we have discussed earlier. So our first example, a steel wire of 20 diameter is bent into a circular shape of 10-meter radius. Okay, suppose this is our circular shape wire. Okay, circular shape wire, and this radius is 10 meter. This radius is 10 meter. Radius is 10 meter. After that, if E the modulus of elasticity, that is Young's modulus or modulus of elasticity, which is equal to 2 into 10 raised to 5 Newton per square. Then next part is given. Then the maximum stress induced in the wire is how much? Okay, so E is given. Radius of curvature R is given. R which is equal to. Okay, R also given. Then diameter is 20 mm. Diameter is 20 mm. So we have to find out y. We have to find out y. So y which is equal to maximum. We have to find out maximum stresses. So this is our circular wire having diameter 20 mm. So this is 10 meter and this is 10 meter. So y which is equal to 20 by 2. Okay. ER, Y given, and we have to find out F or sigma which is equal to how much. So we have to use this basic equation E upon R which is equal to sigma by Y. Okay. So E given, R radius given, Y also given. Okay. So maximum stress which is equal to, see here, maximum stress which is equal to E. Value of E is 2 into 10 raised to 5 divided by. Now suppose we will convert this equation sigma which is equal to E into Y upon R, and after putting values we get maximum bending stress is 200 MPa. Maximum bending stress is 200 MPa. So all three parameters are given and you have to find out only stress. So second half equation here used. This is our first problem. So maximum bending stress is 200 MPa, that is 2 into 10 raised to 2 Newton per square. Option B is correct answer. Then we will see second question. Okay. Second question, a test is conducted on a beam. Test is conducted on a beam loaded by end couples. The fibers at layer CD are found to lengthen by 0.03 mm and fibers at layer AB shorten, okay, by 0.09 mm. Its 20 mm gauge length as shown in the figure. Taking E which is equal to 2 into 10 raised to 5. 2 into 10 raised to 5 Newton per square. The flexural stresses at top fiber would be. Okay. Now here AB and CD, two portions are given. At CD portion, length is increased, and at AB portion length is shortened. So our bending nature is likewise. Bending nature likewise. Okay. This is bending. This is CD portion and this is AB portion. Okay. At CD portion, length is increased by 0.09 mm and here 0.03 mm shorten. Found to be lengthened here 0.03 and here 0.09 mm. So at AB length contracts and at CD portion length increases. And here gauge length is given, that is 20 mm. Gauge length is given 20 mm. Now for this particular, here strain diagram is given. Here strain diagram is given. From top to CD portion distance is 50 mm. From top to CD portion distance is 50 mm. Please observe in figure. Okay. After that, from bottom fiber to AB portion distance is 75 mm. Distance is 75 mm. And here from CD to AB 100 mm. From CD to AB 100 mm given. In this problem, exact location of neutral axis is not given. So we have to find out exact location by using similar triangle tool. By using similar triangle. Suppose from neutral axis to CD portion distance is x1 and from neutral axis to AB portion distance is x2. Now we will apply similar triangle rule for this triangle 1 and this triangle 2. So vertical by horizontal. So x1 divided by 0.03. This 20 gets cancelled. So x1 by 0.03 which is equal to x2 by 0.09. Okay, vertical by divided by horizontal. Now we will rearrange this x1 by x2 which is equal to 0.03 divided by 0.09. So x1 by x2 which is equal to 1 by 3. x1 by x2 which is equal to 1 by 3. Now here x1 plus x2 already we know that this 100 mm is given. So x1 plus x2 which is equal to 100 mm. x1 plus x2 which is equal to 100 mm. Now x1 which is equal to, or we will convert this equation x2 which is equal to 3 times x1. Okay, from this equation x1 by x2 which is equal to 1 by 3. So x2 which is equal to 3 times x1. We will put here x1 plus x2 nothing but 3x1 which is equal to 100. So x1 plus 3 is 4x1 which is equal to 100. And therefore x1 which is equal to 100 by 4 which is equal to 25 mm. So in that way we calculated distance of neutral axis from CD portion. So this distance is 25 mm. Now we will find out strain. Okay, strain at top fiber. We have to find out strain at above neutral axis. So we will consider this portion only. Now, suppose this is our triangle 1 and this is our triangle 2. In between these two triangles, we will apply similar triangle rule. Okay. So x1 divided by strain at this level. x1 divided by strain. So here x1 divided by 0.03 divided by 20, which is equal. Now we will consider this total distance. So x1 plus 50 divided by strain at that top fiber. So epsilon. Okay, strain at top fiber epsilon. Now we will put here values x1 which is equal to 25 and here also x1 which is equal to 25. And after solving we will got epsilon which is equal to 0.00445. Please check this answer is correct or incorrect. This is our strain and we have to convert into stress. So stress which is equal to strain into modulus of elasticity. Already we know that this relation between stress, strain and modulus of elasticity. So F which is equal to 0.045 into 2 into 10 raised to 5 which is equal to 900 MPa. So our option 1 is correct, 900 MPa. Only here similar triangle rule is applied. Okay, by applying similar triangle rule, first we have to find out exact location of neutral axis. Once you got exact location of neutral axis, then you have to find out stresses at top, and at top tension is created. So this option D automatically incorrect because of here compression is generated and we have to find out stresses at tension. So this D is already incorrect option. Now you have to choose from these three options. So for that you have to apply similar triangle rule in between these two portions. This is triangle 1 and suppose this is triangle 2. And from this that you got strain is 0.0045. Once you got strain, you have to find out stress. So stress which is equal to epsilon into X modulus, and X modulus is given 2 into 10 raised to 5. So finally stress which is equal to 900 MPa. 900 MPa. So option 1 is correct. Then we will move towards next point. Next point is beam of uniform strength. Beam of uniform strength. Beam of uniform strength. For that, first I will draw some figures and then I will explain. Suppose this is our simply supported beam. This is our simply supported beam AB, and on that beam, one uniformly distributed load is applied and intensity is W. Suppose this is L. Now we have to draw bending moment diagram for this. So bending moment diagram is circular, and here now you tell me maximum bending moment for this particular figure which is equal to how much? If uniformly distributed load is applied for that particular condition, maximum bending moment which is equal to yes please anyone. Vaibhavi Kamble, what is maximum bending moment for this particular condition? Snehal Patil. निकिता. मैं ऑडिबल ऍटलिस्ट घेऊ मी रिप्लाय. माझा आवाज तरी येतोय का?
Yes, ma'am.
Yes, ma'am.
So what is maximum bending moment value for this particular case?
WL
square by 8.
Good. WL square by 8. So if uniformly distributed load is applied at that time, maximum bending moment is WL square by 8. Now we will see for point load. Suppose this is simply supported beam, and on that beam one point load is applied. One point load is applied. Suppose this is W. This is L by 2. This is L by 2. Now I will draw figure here. Maximum bending moment for this particular case, which is equal to
WL by 4.
WL by 4. Good, correct answer. So see here, if loading condition is going to change at that time, our back bending moment also change. So one equation with you, sigma which is equal to M upon Z. M upon Z. Here M nothing but moment of resistance. MR which is equal to sigma into Z. Sigma into Z. And here sigma nothing but strength or material property. Strength or material property. Please remember, if moment of resistance comes at that time, sigma means you have to consider strength or material property. Don't consider here stress. Okay. So this moment of resistance this moment of resistance proportional to our section modulus, or section modulus is proportional to our moment of resistance. Section modulus is proportional to our moment of resistance. Now we have to find out these formulas. Okay, we have to find out these formulas by applying equation. Suppose we will consider for rectangular beam. For rectangular beam. Okay, suppose this is B and this is D. Now you tell me for rectangular beam, section modulus which is equal to how much? BD square upon 6. How this is what? Okay, our basic equation Z which is equal to I upon Y. So moment of inertia for this rectangular section is BD cube upon 12 divided by y nothing but distance of our depth of neutral axis. So d by 2. So 2 divided by d. 2 ones are 2, 2 6 are 12, and this 1d gets cancelled. So section modulus for this rectangular section is BD square upon 6. BD square upon 6. Now we will put here B is constant. We will put here B is constant. B value is constant. So what is remaining here? D square upon 6, which is equal to D square upon 6, which is equal to MR. Okay, MR. D square upon 6, which is equal to M upon sigma into B. Okay, MR. So we will write here D square, which is equal to M upon sigma B into 6. Okay, 6 by 2. So 2 ones are 2, 2 threes are 6. Therefore, we will take square root D, which is equal to square root of 3M upon 6 sigma B. So M nothing but WL. Okay, WL. So this formula comes. And when we are going to put depth constant, D is constant, D which is equal to constant, then we will get this formula 3WL upon 2F D square. So just you have to remember that when we say beam of uniform strength, if extreme fiber stresses or maximum bending stresses is same at every section along its longitudinal axis. Okay. म्हणजे जर आपला हा बीम असेल तर त्या बीमच्या लॉन्जिट्युडिनल ऍक्सिसला जे एक्स्ट्रीम फायबर स्ट्रेसेस ते सेम असतील तर तो बीम काय झाला तुमचा युनिफॉर्म बीम असेल. दिस इज कॉल्ड एज युनिफॉर्म बीम. Then next, here one example is given. A simply supported beam of span L. This simply supported beam is given having span L carries a concentrated point load W. This point load W at mid-span. So centrally point load is applied. If the width B of the beam is constant, what is constant? B is constant and its depth is varying throughout the span. Depth is varying throughout the span. Then what should be its mid-span depth when design stress is F? Okay. So our first condition, beam width is constant and depth is varying. So from bending equation, bending equation is M upon I, which is equal to F upon Y. So which is equal to maximum bending moment for this particular case is WL upon 4. So WL by 4 divided by moment of inertia for this particular section. For this rectangular cross section, BD cube upon 12, which is equal to F. We have to find out F divided by Y. Y means depth of neutral axis. So d by 2. This is d by 2. So here d by 2. So d which is equal to we got 3 under root of 3 WL divided by 2BF. So which option is correct? Option C is your answer. So just you have to remember this equation. You have to put values and calculate this. But here condition is B is constant. So option C is correct answer for this question. Then next concept related to beams of composite section. Beams of composite section. Now this is important point. So first you remember that composite means member made of more than one material. Okay, if member made of more than one material, then this is called as composite member. Okay, now we will see. Suppose this is our steel material. Okay, this is also steel. And this is wood material. This is wood material. So this particular member is made up of by using two material. So this is called as composite section. This is called as composite section. Okay. Now here one example is given. Modulus of elasticity for first material divided by modulus of elasticity for second material, which is equal to m. So this is called as modular ratio. This is called as modular ratio. So now here we have two equivalent properties. Apply equivalent properties. Suppose E steel, I steel, which is equal to E wood into I wood. E wood into I wood. We will apply this equation. Okay. A steel which is equal to I steel, E steel into I steel, which is equal to E wood into I wood. That means moment of resistance of steel, which is equal to moment of resistance of wood. Moment of resistance of wood. This equivalent concept we have to apply. So how to find out moment of resistance? By using sigma into section modulus. So sigma for steel into section modulus for steel, which is equal to sigma for wood into section modulus for wood. Section modulus for wood. Now we will keep strength of material one side and section modulus one side. So sigma steel divided by sigma wood, which is equal to section modulus of wood divided by section modulus of steel. Section modulus of steel. Okay. So section modulus of steel, nothing but modulus of elasticity into epsilon, strain. So modulus of elasticity into strain divided by modulus of elasticity of wood into epsilon. I will write here sigma S upon sigma W, which is equal to ZS upon ZW, which is equal to Young's modulus of steel into epsilon steel divided by Young's modulus of wood into epsilon wood. Okay. Now we have to equalize or equal to these two values. Epsilon S, which is equal to epsilon wood. म्हणजे ह्या दोन व्हॅल्यू आपल्याला काय करायच्या सेम पुट करायच्या तरच आपला आन्सर काय येणार आहे सेम येणार. सो sigma s upon sigma w, which is equal to es upon ew, which is equal to m, that is modular ratio. So modulus of elasticity of first material divided by modulus of elasticity of second material, this is called as modular ratio. So this is called as modular ratio. This is our basic equation you have to apply here. So modular ratio, which is equal to modulus of elasticity for first material divided by modulus of elasticity for second material. Now see here, you have to find out total equivalent width. Total equivalent width. So how to find out total equivalent width? So this B plus 2 times M, that is modular ratio. म्हणजे आपल्याला इथे काय करायचंय की ह्या दोन मटेरियलचा यंग्स मॉड्युलस सेम करून घ्यायचा, इक्विव्हॅलंट करायचं, इक्विलिब्रियम करून घ्यायचं. So 2m into this t. So this is our equivalent width. So please remember, composite section or composite member means if this section made up of by using two materials or more than one material, this is called as composite section. The next concept is related to fletched beam. Okay. Next is fletched beam. So here this figure shows this timber material, this timber material is given and this hatched portion is steel material is given. Now one different thing is here in fletched beam. Suppose our extreme fiber length is same. Okay, for that I will draw figure here separate and explain you. Suppose this is our structure, okay, and this beam is made up of by using two different materials. So this hatched portion is steel and this portion is timber. So this is fletched beam. Now I will draw strain distribution diagram. Okay, strain distribution diagram for steel. So sigma steel and here also sigma steel. And now I will draw for timber. So sigma T and sigma T. Now see here, depth of neutral axis is same for both materials. म्हणजे above neutral axis आणि below neutral axis. म्हणजे टॉप फायबर असू देत किंवा बॉटम फायबर असू देत, डेप्थ ऑफ न्यूट्रल ऍक्सिस काय आहे, सेम आहे बोथ मटेरियल साठी. त्यामुळे जर आपल्याला मुवमेंट ऑफ रेजिस्टन्स, इफ डेप्थ ऑफ न्यूट्रल ऍक्सिस इज सेम ऍट फॉर two materials, at that time we have to find out MR total, which is equal to MR1, moment of resistance for first material, plus moment of resistance for second material. Okay, so moment of resistance total, which is equal to moment of resistance total, which is equal to moment of resistance for steel plus moment of resistance for timber. So if the depth of neutral axis or extreme fiber length is same, at that time this formula is applicable. म्हणजे जर हे दोन मटेरियलची डेप्थ सेम असेल तरच आपण हा फॉर्म्युला ऍप्लिकेबल यूज करू शकतो, अदरवाइज इट इज नॉट ऍप्लिकेबल. जर तुमचा बीम तयार होत असेल एका मटेरियलची हाईट जास्त आहे आणि दुसऱ्या मटेरियलची हाईट कमी आहे, सपोज दिस इज अवर स्टील अँड दिस इज अवर टिम्बर. नाउ सी हियर बॉटम फायबर, at bottom fiber depth of neutral axis is not same, so this formula is not valid. If depth of neutral axis is same, at that time you have to apply this formula, moment of resistance total, which is equal to moment of resistance for first material plus moment of resistance for second material. Okay. आणि हे हा फॉर्म्युला कधी वापरू शकतो आपण, इफ एक्स्ट्रीम फायबर लेवल्स आर सेम. ओके, नाउ Suppose this moment of resistance for steel. How to calculate? So sigma for steel into section modulus for steel plus sigma for timber into section modulus for timber. Okay. So sigma s divided by sigma t. You have to apply here basic concept. Already we have studied this basic concept. Sigma s divided by sigma t or sigma w, which is equal to es divided by ew, which is equal to modular ratio. Es by ew means modular ratio. So sigma s, which is equal to m into sigma w. Okay, m into sigma w or es, which is equal to m into ew. म्हणजे आपण इथे काय केलं हे es modulus of elasticity for steel, which is equal to modular ratio into modulus of elasticity for wood. Okay, modulus of elasticity for wood. Now see here, two steel plates are given. Two steel plates are given. So stress 2 times 2 into sigma s zs divided by 2 into sigma s zs divided by 6 plus here for timber only 1. So sigma w into zs. Zs is b is given and d is given. See here, for this particular member, for this particular timber, b is given. So b d square upon 6, and I will write here for steel also z value from figure 2 into sigma s and z for this steel. So t into d square divided by 6. 2 into d square divided by 6. Now we will put value of this sigma s. We will put value of this sigma s. So 2 into value of sigma s is m into sigma w. M into sigma w t d square upon 6. T d square upon 6 plus remaining part as it is. Sigma w b d square upon 6. Now we will take sigma w d square by 6 common. So sigma w d square upon 6. So what is remaining in bracket? 2m into t plus b. 2m into t plus b. So moment of resistance, which is equal to sigma w b1 into d square upon 6. That is b1, which is equal to b plus 2m. This equation comes. Okay, got it? How to find out or how to derive this equation? Two different materials are given. 2 steel plates and 1 timber plate is given. So extreme fiber length is same. Therefore, moment of resistance total. That means moment of resistance in steel plus moment of resistance in timber. Moment of resistance, how to calculate? Strength of material into section modulus. So steel plates, 2 plates are given. So here 2 is written. Then for timber, only one member is given. So sigma w into section modulus for this b into d square by 6. And for this steel plate, t into d square. And after putting sigma s, which is equal to m into sigma w, we will get this final equation. Okay. This is our flitched beam concept. In that, you have to remember that this equation is valid for if extreme fiber length is same. Then and then only this equation is valid. Otherwise, it is not applicable. Then we will move towards next point.